I'm Peter Linington. I'm from the University of Kent, and my role in this project is to investigate the storage technologies that are available and which ones best fit the requirements of the project. In the original EDSAC, mercury delay lines were used. A variety of sizes. This is a very small one from the original EDSAC machine. This stored numbers as a sequence of bits. Bits came on an electrical cable at this end and excited a quartz crystal, which produced a series of sound pulses travelling down a column of mercury to another crystal where they generated an electrical signal that was fed out. A number could be stored for as long as needed by going repeatedly round and round this loop. Now, these systems, particularly the larger ones, this is only a very small example, proved in practice to be rather unreliable because it was difficult to make this assembly of the mercury and the crystals in it sufficiently reliable. And there are also issues nowadays about the health and safety aspects of using large amounts of mercury in the machine. So for both these reasons, we feel we cannot replicate this in quantity. Therefore, we looked at other storage technologies.
To see which technology the EDSAC project has decided to use, we visited Peter in his home at Canterbury.
This is an example of a wire delay line dating from the early 1950s. The idea is very similar to the idea of mercury. The way it works is that an electrical signal actuates a coil here, and that coil induces a magnetic field in a pair of nickel tapes. The tapes then contract based on a property of nickel called magnetorestriction, in which the dimensions of the nickel change when a field is applied to it. The result of this is that a sound wave passes along the tapes. One of them is pushing and the other is pulling, so that when the two sound waves reach this steel wire, where they're welded on to opposite sides, they twist the wire. The wire goes around in a spiral until it comes out at a receiving unit. And at the receiving unit, we convert the sound waves back from a torsional form into a longitudinal form in this pair of tapes, and a coil here picks up the motion of those tapes, and that signal is picked up, amplified, and goes to be cleaned up and reinserted at the beginning of the line.
Making the pairs of induction coils which excite the nickel tapes is a fiddly business, involving an underlying plastic former, coil retaining barriers, and colour-coded positive and negative sleeves. Each coil is wound using wire just 0.04 of a millimetre thick, and making use of a homemade rig based on a Black & Decker screwdriver.
We then mount the coil into its clip, attach the wire loosely to the thicker mounting wire, solder up the joint, add a second coil of the opposite polarity in the second slot, and we have a completed transmitter unit.
Peter also has to make the nickel tapes himself. The first stage is to take a nickel wire and pass a current through it to anneal it. This softens it to make it easier to roll.
The next thing we do is take the wire that we've done the preliminary annealing on and use this rolling mill which Burton fabricated and pull the wire smoothly through the rollers, which flattens it to form a tape. But it's been again work hardened to a certain extent in that process, so we put it back into the clips and apply the current to re-anneal it.
Peter now has the first working prototype delay lines.
The signals come in here and are used to drive a coil assembly here. The coils excite pulses in the nickel tapes here. If there is a need to trim the delay, this coil unit slides up and down on a pair of rails so you can change the effective length of the delay line. The nickel tapes are carried to a weld at this point where they convert the longitudinal waves in the tape to a torsional wave in this steel wire here. Some part of the sound energy is reflected at this point and comes back, and this unit here is essentially an echo suppressing buffer that absorbs any stray. The main pulse, however, carries on down the steel wire, round the spiral, and ends up here, where another set of welds attach 2 more tapes, and the torsional mode is converted into longitudinal pulses, which are picked up by this coil here and taken off to a preamplifier via this socket here. The size of the pulses that come out from the receiver are much smaller than the input, and so the next stage is an amplifier that increases the amplitude of the received signal about 10,000 times. This box contains a short delay line, actually an 18-bit delay line of the kind used internally to the computational part of the machine. Signals arrive along this red cable here and are fed into the delay line, and the result is a series of pulses coming out on this green cable to this box. Here the pulses are reshaped and ANDed with the clock pulses from the data generator. On the oscilloscope we can see 2 traces. The top trace is the test data which is being generated. It takes the form of pairs of pulses repeated every 18 pulse intervals. This is what's being fed into the delay line. The lower blue trace is the result of the data received from the delay line after some preliminary cleaning up has been done, and this delay line unit has operated for several days without errors. In addition to checking the correctness of the repeating pattern, we also need to check that the store responds correctly to all zeros and all ones. For all zeros, we're interested to see that the store remains empty even though there is other electrical noise that might induce errors. For all ones, similarly, we want to apply a continuous pattern and see that that is maintained for a period without dropping any bits. One question that's often asked is, why do we use sound waves? It's an electronic system. Why don't we just use long wires to delay the pulses? Now, the delay in the EDSAC is about 1 millisecond. And for sound waves travelling through mercury, that corresponds to a little over 1.5 meters. If we were to do the same thing with electrical pulses in a wire or optical pulses in a fibre, the fibre we would need would be 200 kilometres long. And this brings its own problems, and certainly is not something that Wilkes would have available to him with the technologies of the time.